My name is Ross Kern, and today we're going to be talking about phase diagrams. Some of the things we're going to cover in this video: what is a phase, the components of the phase diagram. We're going to be able to calculate composition and the concentration of phases at a point, eutectic microstructures, and we're also going to talk about calculating eutectic composition. What is a phase? A phase is a homogeneous portion of a system that has uniform physical and chemical characteristics. So, specifically, if we're to talk about an example such as H2O, and let's see, liquid water and solid water, so ice. They both have the same chemical composition and chemical formula, but they have both distinctive physical properties. So those are two different phases. Whereas another example would be graphite, which is pencil lead, and diamonds. Both of them are made of pure carbon. They both have the same molecular formula, but the way they're bonded gives them distinct chemical or distinct physical characteristics, which defines them as two different phases. Diamond is very hard and rigid, and graphite is very soft and malleable. So, this is an isomorphous phase diagram, and this is because there's complete solid and liquid solubility between the two components. As you can see on the bottom, it's completely solid at the very bottom, and the very top it's completely liquid. Some of the components: the x-axis is the composition with respect to weight percent nickel, which means on the right side of the graph is 100 weight percent nickel, and the left side is 0% nickel. On the other hand, the left side of the graph is 100% copper, and the right side of the graph is 0% copper. The y-axis is in temperature, but it doesn't have to be temperature. It could be multiple things like density, for example. This is the solidus line, which is where the alpha region, is an alloy of, or it's the composition between copper and nickel. The solidus line is where it begins to melt, and the liquidus line is where this material finishes melting, so it's completely liquid at the liquidus line. So at point A, how many phases are present? 1. It's in the alpha region, so there's only 1. Whereas if we were to talk about the solidus line, point B, or the liquidus line, since they are touching or inside of a two-phase region, there's 2 phases present at those points. And point C is completely in the liquid region, so there's only 1 phase. So let's talk about how to calculate composition and concentration at this point B, which is 35 weight percent nickel and 1250 degrees Celsius. First, we start off by drawing a tie line, which is a straight line horizontal from point B to the left and the right until it intersects the liquidus and the solidus line. And if we want to find out the composition of the liquid phase, we find the intersection with the liquidus line, draw it straight down, which is 31 weight percent nickel. And that is the composition of the liquid phase at B. And same thing for the right side, where it touches the solidus, is the composition of the alpha phase at this point B. Now, if we wanted to calculate concentration, or how much of each phase is present at this point, we use something called a lever rule, which in short means we divide this line into 2 pieces, and we call the total length of the line C. So A, B, C. And to calculate the concentration of the alpha phase at B, we take the line segment opposite of the alpha and divide that by the total length of the line, so it's A divided by C. And if we wanted to calculate the if we wanted to calculate the concentration of the liquid phase at B, we take the same thing, the opposite line segment from the liquid phase, and divide that by C. Please pause it now if you want to look at the calculations. This is a binary eutectic phase diagram. So let's go ahead and go through the components. There's the solidus lines, as I mentioned before, between alpha and alpha plus liquid or beta plus liquid regions. Liquidus lines. And we have a new line, solidus, which is between the solid alpha or beta phase and the alpha plus beta phase. We have a eutectic line. So at this point, this horizontal line is where the eutectic reaction occurs. I'll be talking about this a little bit later, but just know that it's called the eutectic line and that this is called the eutectic point. And this whole line and this point touch both the alpha plus beta region and the liquid, so 3 phases. So at A, how many phases are present? It's in the alpha plus beta region, so 2. At here, the solvus is touching the alpha plus beta region as well as alpha, so still 2. Solidus, 2. Liquidus, 2. And at this point, as well as along the whole line, it's touching the liquid region, or a region that has the liquid phase as a component in it, and the alpha plus beta region. So as a total, 3 phases are present along this line. So let's calculate the composition at this point, right there. So first off, we draw a tie line until we intersect the liquidus and solidus lines. We draw them straight down to find the composition of whether or not we're interested in the alpha phase or the liquid phase, which is 17 and 49 weight percent tin, respectively. And then to calculate the concentration, or how much, we divide it up into 2 segments, A, B, the total length of the tie line being C. And same thing before, where we take the opposite side of the line and divide it by C to find the composition of that phase. Please pause it now if you want to look closely at the calculations. So this we're going to talk about microstructures. This is particularly nice to see because it physically, like if you were to take a magnifying glass at this for this material and zoom in on it, this helps show you what would be here. So in the liquid phase, it's completely liquid, so it's just a blob of just of just liquid. So there's no real chunks or anything in there. Whereas once you pass through the liquidus line, it begins solidifying, so you start getting alpha chunks accumulating in there. Once you pass through the solidus line, you start getting alpha chunks, or the alpha chunks completely cover the material, so it's all alpha right now. But once you enter the alpha plus beta region through the solvus line, you start to get slivers of beta mixed in with the alpha chunks. Now, same thing, but this time let's do it from a different point in the phase. So the very top, liquid, at point K and point L, it's still the alpha and the liquid. It just, the chunks are starting to solidify and get together. But once you pass through this eutectic line and reach point M, all the liquid solidifies to this eutectic microstructure, which you can see here. It still retains its alpha blobs, but now instead of liquid, it's surrounded by this like pattern of alpha and beta slivers. Now let's talk about it. What happens if it goes to the eutectic point? So at H, it's in the liquid, so it's completely liquid, as we talked before. Now what happens if it passes through this without entering the alpha plus liquid or the beta plus liquid region to straight through the eutectic point, through the eutectic reaction and reaching the alpha plus beta region? So it completely solidifies into this eutectic microstructure. And this is important part of phase diagrams, just because if you were to look over here at it's different variables, one's tin and one is nickel, but it's still the same concept. At this eutectic point, right below it is where you'll find the greatest tensile strength for this material. So it's very important to know if you're making materials for the real world where this eutectic point is exactly. So you know what composition and what temperature you should cool it at. So now let's say we wanted to calculate how much of this alpha plus beta region is eutectic microstructure. And we do the same thing. At this point, we draw a tie line from where it intersects the alpha region. But instead of going towards the beta region, we stop at a point, or at a line just below the eutectic point. We draw a line straight down to find the compositions for each. And similar things as we did before, using the lever rule to calculate the compositions of the alpha phase and the eutectic structure at this point. Please pause it now if you want to look at the calculations. So what have we covered? We covered what a phase is, the components of the phase diagram, the temperature, and the alloy we're now hopefully able to calculate the composition and concentration of the phase present given a point or given a temperature and alloy composition. We talked about eutectic microstructures, and we talked about calculating eutectic composition. Thank you for your time. Have a good day.